All right, so this is our final set of videos before spring break, and we're finally going to explain why the heck we care about integrals and find the area under curves at all. All right, and we're going to relate it to position, velocity, and acceleration, which is something we talked about with derivatives earlier in the year. All right, so we saw before that if we start off with a function that gives our position at a certain time, all right, these should probably be t's instead of x's, because most of the time when we're talking about these physics applications, we're talking about time being our input. Throughout different times, we have a different position. If we take the derivative of position, we're going to get velocity, so how what direction we're moving in at each time. If we take the derivative of velocity, we get acceleration, which is how fast we're accelerating in each direction. And then I like the third one just because it's got a funny name. All right, if you take the third derivative of position, which is also the derivative of acceleration, you get the jerk, which is kind of pulling you towards a certain direction. All right, so we know this kind of process that if I just go down with derivatives, I get the next type of thing, what's happening at each given time. All right, now we're going to see a formula that'll kind of help us relate this to integrals. All right, so the formula is called the net change formula. And it says, if I start at a, all right, my function value when I plug in a, if I add the integral from a to b of its derivative, that gets me to my function value at b. So if I start at like this point, all right, and I know my integral of a to b at the derivative is, say it's 2, then when I get to f of b, it's going to be 2 higher. So it's kind of an interesting formula, but really if you just rewrite the terms, if I just subtract this a over, this is basically the fundamental theorem of calculus. If I take an integral, that's the difference in the antiderivative when I plug in these two values. So really if I just move this a over here, that gives me this net change formula. So if I start at my function value at a, add this integral, I get my function value at b. It's just basically another way of rewriting the fundamental theorem. But we can use an integral of the derivative to kind of get us between 2 points. All right, but this is the way we're going to kind of think about this net change formula to relate it to acceleration and velocity. All right, so using this information, we get this thing. So acceleration would be our f prime of x, and velocity is our f of x. All right, so if we take the integral of acceleration, then that's going to be the difference of the velocity, so net velocity, the difference in velocity from kind of the start to the finish. All right, same thing, if I take the integral of velocity, I go backwards a step from my relationship, and that gets me to position. So if I take the integral of velocity, that's going to give me position. So another way of thinking this, the area under a velocity function is how far you've gone. So that's the reason we care about these areas, because it allows us to go backwards from these things that we were doing the other direction with derivatives. So if I take the derivative of position, I get velocity. So if I take the integral of velocity, I get position. It allows us to go both ways. So if I have these pieces of information, I go backwards to the other piece. So that allows us to do problems like this. We have this particle, and we know exactly how fast the particle is moving at any time t. We're going to find the displacement, which just means how far the particle has gone from 0 to 3. All right, so using that net change formula and what we know, if we try to go from velocity to displacement, which is a position, a distance thing, we said do the integral from 0 to 3 of 3t, I can write correctly, 3t minus 5 dt. Again, the dt just means t is my variable. All right, now using the fundamental theorem, we can do this without using areas. Or we're still technically doing areas, but we don't have to draw the picture. We find the antiderivative first. Add 1 to the power, divide by the new power, and add 1 to the power, divide by the new power. All right, so that's the reverse power rule. And then we have this notation. I can do this antiderivative evaluated at 0 and 3. Again, remember that just means you put in 3 into this expression, you subtract when you put in 0 into this expression. So now the next thing we're going to get is when we put in 3. All right, that's our first part. Subtract when we put in 0. This case, fairly straightforward. The whole second term is just a bunch of zeros, so that cancels out. And it's just simplifying. Right, 27 over 2 minus 15, which is 27 over 2 minus 30 over 2, and that's negative 3/2. All right, so from time 0 to time 3, my particle is going to be negative 3/2. So whatever the unit ends up being, let's just say it's feet. It's going to be negative 3.5 feet behind where it started. So let's just say if you're moving kind of east is positive, west is negative, it would be negative 3.2 to the west of where it started, because we're going in the negative direction because of that negative sign. The basic idea, just know that the particle is given, we get the velocity of the particle, so we take the integral of that to go backwards to the position information, which is displacement. Just means that how does the position change from where it started. It's a slightly different question than how far is the total distance that the particle traveled, because in the last example, maybe the particle started here and it went east and then went west and then it went east and then went west and it ended up negative 3/2 to the left. Right? But that's different than trying to figure out exactly how far it traveled back and forth. So for this one, we basically don't want to do any of the negative values because we want to know, all right, as we go to the positive, that's some distance traveled. As we go in the negative direction, that's also some distance traveled. So the basic idea is we're going to do the same problem, but we want everything to be positive. So we're going to do from 0 to 3, 3t minus 5 dt. So if we want everything to be positive, technically we're doing the absolute value of that. All right, so that's technically what you're doing. We won't actually do kind of the integral of 3t minus 5. Right, instead, we'll think about it this way. 3t minus 5, if you just kind of visualize the graph of it, all right, it's going to look something like this. So at one point, before this x-intercept, it's all negative. After that x-intercept, it's all positive. And where is that x-intercept going to be? It's when my function is exactly equal to 0, which is at 5/3. All right, so at 5/3, my function changes from negative to positive. So that's going to tell me I'm going to do the integral from 0 to 5/3. All right, that's going to give me this negative piece here, 3t minus 5. All right, that answer is going to give me the negative green area that you drew, so I'm going to multiply by a negative to make it positive. I'm going to add the integral from 5/3 to 3 of the same function, dt. And that'll give me this yellow positive area. All right, so I'm going to get the yellow positive area, which is just our normal integral. This area would give me a negative answer, which would cancel out with some of the yellow, but I don't want it to, so I just add this extra negative sign at the front to make sure it turns into a positive. I'm adding stuff together instead of it canceling out like I did in the previous problem. So now my answer, this is going to be negative 3t, oops, use the correct antiderivative, 3/2 t squared minus 5t. All right, evaluated from 0 to 5/3. I'm going to add 3/2 t squared minus 5t, evaluated from 5/3 to 3. All right, so now, again, the 0 part of this is going to end up going away. So now it's take the 0, subtract. When I plug in 5/3, I'm going to plug in 5/3. 5/3 squared minus 5 times 5/3. And the second one, I'm going to plug in 3 first. All right, and then subtract when I plug in 5/3. And then after this is going to be a bunch of simplifying, other than the one mistake I made. I put a t when I'm trying to plug in 3. So in the basic idea, I take the antiderivative. This one I plug in 5/3 and subtract when I plug in 0, but we already saw when I plug in 0, I get 0. So that's why I just have this one. Here I plug in 3, subtract when I plug in 5/3. All right, so those are my kind of 3 different pieces. And then it's just going to be a bunch of simplifying. So I'm actually just going to pause the recording and write down all the things so I'm not saying a bunch of random numbers. Okay, so I added a lot of stuff. So I had these expressions, all right, simplified by just multiplying everything out. We have all these different fractions, so I just got everything over the same common denominator 6 and just combined all the like terms until I get to this final answer. If you were to put that in a calculator, you get this decimal approximation. All right, so what does this mean? I found the integral from 0 to 3 of the absolute value. All right, just making sure everything's positive. That gives you total distance traveled because nothing's going to cancel out. But in practice, what does that mean? It means I take the stuff that would give me a negative area and I want to make it positive, so I just put this extra negative sign in front to flip that negative to a positive. That stuff that would already be positive, like this yellow area, I just keep that as my normal plus sign. So when I get down here, I end up having a negative answer here with that negative sign there. Those cancel. So this is would have been this negative green area, but now it's positive. This thing here is that original yellow area. Those combine and give me this answer there. All right, so just kind of simplifying a bit. There's a lot of simplifying and plugging things in. But the basic idea remains, you just want everything to be positive. All right, so nothing cancels out and you get the total distance traveled. So you can see it actually traveled about 6.8 units, but at the end of the day, it ended up negative 1.5 units to the left. So there was some of this kind of canceling out when it went back and forward, until it ended up just a little bit to the left of where it started out.